Hi, how are you doing? I'm Mohammad Sadri, postdoctoral researcher at Electrical Engineering Department of TU Kaiserslautern. This is video number 9, and these are my homemade hobby videos regarding ZYNQ device. In these videos, I'm sharing my experience and whatever I know about ZYNQ device with you. These videos are not official, and I'm just creating them for myself, but I believe if you watch them, they can help you to accelerate your learning with ZYNQ device. So this is lesson number 9, and this is the first video I'm creating for lesson number 9, and actually I have called it software development for ZYNQ using ZYNQ SDK. And in this series of videos related to lesson number 9, I am going to discuss how you create a very simple software running on the ARM host of the ZYNQ. So you have already seen this block diagram several times. This is actually somehow representative of ZYNQ architecture. We have the PL, we have the PS, we have our hardware accelerators on the PL, or the logic that we want to implement on the FPGA side, we have here on the PL, and then on the PS, we have our ARM CPU cores that they will run the software that we want. Through these XI interfaces that we have here on the boundary of PS and PL, these two will share data. Usually, for sharing data, they can use the DRAM memory, which is at the PS side, or they can use the on-chip memory or L2 cache. Actually, I have given a detailed description on this in lesson number 8. So if you have not watched lesson number 8 and you want to learn more about the architecture, please refer back to lesson number 8 and first watch that video. Okay, now on the ARM host, we can run different types of software. For example, we can run a bare metal system, indeed a standalone application that will be executed directly by the ARM cores. Or even on the ARM cores, you can easily run the Linux operating system. A full Linux operating system can be running on the ARM cores, and actually the Linux kernel can handle for you both of the cores and can schedule different processes to different cores, and it looks like a complete computer. In addition, you may like to run FreeBSD on your ARM hosts. There exists the possibility of also running FreeBSD on the ARM host of the ZYNQ device. And why you should do that? Maybe for licensing issues, for example. Maybe you are creating a kind of commercial product for which you want to really limit the access of other people to the source code and to the design that you have done. Furthermore, you can run the Windows operating system, indeed the Windows embedded operating system on your ZYNQ device. But for now, for this specific video, we will focus mostly on the bare metal, on the standalone mode, in which we have a simple application that we will develop in C. We will compile it using the cross-compilation toolset that ZYNQ provides to us, and then we will run that on our ARM host. And later in other videos, I will focus also on running Linux operating system on the ZYNQ device, and hopefully I will cover also running the FreeBSD on the ZYNQ device. But for now, our target is bare metal. So I will run the bare metal. I will directly run an application on my ARM CPU cores here, and indeed for this example, I will just use one ARM CPU core. I will not use both of them. So the first ARM CPU core will be running my application, and actually we will have some hardware here on the PL. The hardware produces some data and copies the data over these XI interfaces to the DRAM memory, and then the software that we will run here on the ARM host will read this data, will have access to this data. So what is the system and indeed the hardware that I want to implement here on the PL? Here is a very simple block diagram of the hardware that we are going to implement on the PL. Actually, the blocks that I am showing you here, you know them all. Indeed, in the previous videos, I have covered all of these components in enough detail, so none of them should be strange or new to you. Here we have the sample generator, and for the sample generator we covered it in lesson 7, where we were talking about developing XI stream interfaces using pure RTL flow. So if you have not watched that videos, maybe it's a good idea to go back and watch those videos and then come back here. So I have the sample generator. Actually, the sample generator is an XI stream component. It has one XI stream slave interface, one XI stream master interface, and for now, for our example design, I'm not connecting the slave interface to anywhere, but the master interface will be actually connected to an XI DMA. The XI DMA, as I have described in lesson 7 and previous lessons, is responsible for receiving my XI stream data and then copying this data to a suitable location in the DRAM memory. So the XI DMA is responsible for converting my XI stream interface to an XI memory mapped interface. Then I have one XI GPIO block in my design. As I have described in lesson 7, there are a set of configuration signals available for our sample generator. Through these configuration signals, you can enable, disable the sample generator, and you can indicate the frame size of the data that the sample generator produces on its output. Indeed, the frame size is indicating where the T-last signal of XI stream interface should come. I have put this XI GPIO unit here, and this guy is responsible for driving these signals. So here we have the main component of our system. This is the ZYNQ PS. The ZYNQ PS contains, as I have described to you in previous lessons, the ARM cores. Also, it contains the DRAM controller. Our DRAM modules, our DRAM chips are connected to this DRAM controller. There exist the XI interfaces through which the data will be transferred from the PS to the PL and from the PL to the PS. To be more specific, for this design, I will use the HP0 XI memory mapped slave interface for transferring data from the PL to the PS. And for this design, I will use the GP0 XI memory mapped master interface for transferring data from the PS to the PL. For which purpose do I use the GP0? The purpose is indeed to configure the XI GPIO and also to configure the XI DMA. What kind of configuration do I write through GP0 to each of these units? Well, for XI GPIO it is very simple. For XI GPIO, through this port, I will first set the port of XI GPIO as output port. Then, when it is configured as output, I will put suitable values that I want on these signals. Then, for XI DMA, I need to configure it and I need to tell to it to which memory address here on the DRAM it should write the data that it receives over this AXI stream slave interface. Indeed, the AXI DMA by itself, it doesn't do anything. It should be programmed by your ARM cores through this GP0 port so that it can begin the operation. And what is the main configuration that you should indicate is the amount of data that you want to transfer from this AXI stream slave port to DRAM and the address to which the write operation should happen. These numbers should be written to AXI DMA unit, and then after you have configured the AXI DMA with suitable values, it will begin the transferring data to the DRAM memory. So we have one AXI memory mapped master interface which is connected indeed through an AXI interconnect to the HP0 port. I have not drawn the AXI interconnect unit for making the block diagram simpler. And then there is one very important point. Whenever the AXI DMA unit is finished with one transfer task, it should somehow inform the ARM cores that you have on the ZYNQ PS that, look, I have finished the transfer task, come and reprogram me and define for me a new transfer task. So, for example, suppose that through this GP0 port, you configure the AXI DMA to transfer 1 megabytes of data. When 1 megabytes of data is transferred, an interrupt will be generated by AXI DMA to the ZYNQ PS. And then when your ARM cores they see the interrupt, they should go and reprogram the DMA engine to continue transferring the data. I have talked about AXI DMA in detail. I have told you that AXI DMA can have a simple configuration in which for every transfer you should configure the AXI DMA unit, or it can operate in a scatter-gather mode. For our example, for now, we will cover the simplest possible situation so that we can understand the concepts easily and we can perform our tests. So I create this hardware inside the Vivado environment, and then what I will do, I will go through synthesis, I will go through implementation, and I will generate the final bit stream for this guy. And then after that I switch to ZYNQ SDK environment and I begin creating a code that we will run on our ARM cores. And what will this code will be doing? Indeed, this code will do several tasks for us. Indeed, as I told you, it is a bare metal software. I will run it on the ARM host. And the code that I will write first initializes the system. Indeed, the PS of the ZYNQ has a very large number of registers, and in order for the PS to operate correctly, you need to first initialize these configuration registers at power up. Don't worry, the ZYNQ SDK will produce the default values for all of these registers automatically for us. So all my bare metal application will do is just to copy these values to their specific location on the registers of the PS. Then my bare metal application enables the PL clocks and also the interfaces between the PS and the PL. Indeed, when you turn on your ZYNQ device for the first time, the clocks that go from the PS to the PL, they are not enabled. And the interfaces that we have between the PS and the PL, they are not enabled as well. Indeed, there are a set of level shifters between the PS and the PL which are disabled. So by default, when you power up the ZYNQ device, you cannot really transfer data between the PS and the PL unless you enable these axial level shifters and you enable the clock signal which is going from the PS to the PL if you are using that clock in the PL. So this is one task that our bare metal software will do. And then our bare metal software will program the Axi DMA engine, and it will instruct the Axi DMA engine to perform data transfers to a suitable physical address in the DRAM memory. After this programming is done and the Axi DMA engine is ready to transfer the data, the program that we will write will enable the sample generator so that it begins sending samples to the Axi DMA engine. Okay. So, for the first time in this series of lessons, I will try my system practically on a Z board. So, I will not show you actually the Z board itself, but it will be connected to my computer like this. Indeed, we will have two connections through two USB ports of my laptop. So, one connection will be for UART interface that we will use as a console, and the output of our printf commands that are executed by the ARM host, they will be transferred over this UART interface to my notebook so that I can see and I can debug what the ARM cores are doing at each moment in time. And then I will also have another connection from my notebook to the Z board, and this will be actually get connected to the Jtag interface of our ZYNQ device. And as I will show you through this Jtag interface, I will do all of the tasks that I need. Through this Jtag interface, I will first program the PL of the ZYNQ with the bit stream that I have obtained during hardware implementation. Then, through this Jtag interface, I will transfer my executables to the memory so that I can execute them on the ARM host. Then, over this Jtag interface, I can debug my application which is running on the ARM host. And finally, over this Jtag interface, I can debug my hardware. I'm not sure if in lesson 9 I show you debugging the hardware. Maybe I create a separate lesson for that, because actually that is very important. But the rest of the things I will show you through the videos that I create for lesson number 9. Okay. That is it for now. This was the introduction to lesson number 9, and I would like to thank Daniel Mastio for in fact sharing a license for Vivado environment for the Z board with me, and in fact he has gifted me a license, a complete license for Vivado, and Matthias Dubon has gifted me a Z board, and I would really like to thank these two guys because of their support. Then I would like to thank Professor Norbert Wayne of TU Kaiserslautern because of his support, and Professor Luca Benini of ETH Zurich because of his support. Without their support, these videos would never have come into existence. I like to remind you that you can always find the latest materials related to these courses, the latest files and design examples related to these courses on my two websites. The first website, green-electrons.com, and then the second website, googlia.com. Actually, at the moment they are the same, but I think in very near future they will be slightly different. Okay, that is it for now. This is the introduction of lesson 9. Now let's get started. I will go through the Vivado environment. I will design our hardware. I will go through synthesis implementation, and I will show you the flow, how you generate bit stream inside Vivado environment. That is actually simple, and I think you can do it yourself. But then after that we go to the ZYNQ SDK environment and we begin developing the code for the ARM host. And our code, it will contain many important parts. How you configure the AXI GPIO, how you write to AXI GPIO, how you configure the AXI DMA, how you transfer data to AXI DMA, how you handle your interrupt. I think these are very important concepts that you need to learn. Okay, thanks for watching this video. Once more, I'm Mohammad Sadri, postdoctoral researcher at Electrical Engineering Department of TU Kaiserslautern. See you in the next video. Bye.